here molecule or atom to mole, okay? So let's say that you know maybe you're working with really small quantities for some reason, and this is more for an experimental purpose rather than, say, an industrial purpose. And so you have molecules. So if you have molecules, then what part of the chart are we looking at? Well, we're looking to start way up here, right? And so if you're just going from molecules to moles, first you need to get your molecules of your substance to moles of your substance, and then you use the balanced equation to get to moles of the actual substance that you're looking for, right? So again, we need to have a balanced reaction. So that was 2 and 2. And as always, we start with the number that's given us, 7.56 times 10 to the 24 molecules of CuO. And we're doing it twice. Okay, and so first we need to get that to moles of CuO if we're going to use the balanced reaction. So molecules has to go on the bottom if it's going to cancel out, right? And we know that to get between molecules and moles, we've got to use Avogadro's number. And so that's got to be in the bottom. And 1 mole on top. Those will cancel out, right? That's the point. Now that we've gotten to our moles of copper oxide, we can now use the balanced reaction to use the mole ratio to get us between the moles of our copper oxide, which are here, to the moles of carbon, and then the moles of carbon dioxide, which is what we want. So to get to moles of carbon, we first need to put moles of carbon in the, copper oxide, so that they cancel out. That has to be for both of them. Now we use the mole ratio. It's 2 to 1 for carbon, which is our problem on the top. 2 to 1. And it's 2 to 1 for carbon dioxide, which is on the bottom here. 2 to 1. So again, we're two problems that are essentially the same, but that's just by luck because the mole ratios just happen to be the same. So our math, at least, is the same, is essentially what we're doing here. So 7.56 divided by 6.022 divided by 2. This is going to be a 3 sig figs. I get 0.628. That's going to be 24 minus, because of this guy, 23, which gives us 1. So that'll be our exponent, times 10 to the 1. We want to put this in proper scientific notation, so we move our decimal over to the right, which means we reduce, which takes that to 0, which means we can get rid of that altogether, which means I have 6.28 moles of carbon here, and that's going to be the same here, 6.28 moles of CO2 that are produced. So there's a molecule or atom. If we had atoms for our reactant, it would have been the same process.